I want to show you the last step on our journey, looking at resistive circuits. And I want to show you how you would take a really complex one like this, and using just the things that we've learned in the past, break it down, figure out how to simplify and find all the voltages and currents in here. What I'm going to do is I'm going to use purple for the resistors, I think, for the resistances. So I don't have to have all the ohms, because it's going to get busy. It's going to get really busy. Now, we're doing a couple things. First thing you're going to do is simplify and redraw the circuit. So you're going to identify where you have parallel resistors you can combine, or series resistors you can combine, and you're going to replace those with new equivalent resistances. Then you redraw the circuit and repeat. So you're going to just keep doing that first step over and over and over until you wind up with one voltage and one resistance. Okay? Then you can start working back. And interestingly, with in some circumstances, you don't have to go all the way to one resistor. You'll be able to see that you can solve the currents and voltages if you get it close. But here we go. So I'm going to start off here, and I'm going to grab a calculator. And the first thing I'm going to do is redraw this circuit, but with those replaced with an equivalent resistance. So I'm going to still have 20 volts. I'm going to draw it a little smaller here. And 5 ohms and 4 ohms and whatever that equivalent is, and 2 ohms down here. Okay, same connections, but I've just replaced those 3 with that one. Same connection here, right? It's still got to be connected up here and down here. Okay, so that's my new equivalent resistance. And once again, 5, 4, 2. And when I do this, and again, it's really nice to be able to do this on a calculator. 1 inverse plus 6 inverse plus 10 inverse equals 0.789. 0.789 ohms. Again, I'm leaving the units out because it's going to get crowded. Simplify and redraw. Hey, look at that. That's in series. Okay, so I'm going to redraw it. And I really recommend redrawing it each time, because we're going to need to see what these connections were and how voltages and currents related. 4.789 when we work backwards. 4 plus 0.789. Now I do that in parallel with a 2 ohm resistor. And I get 1.41 ohms. And each step, does this make sense? 5, 20 still, 20 volts. And what did I just say? 1.41 ohms. And you can see the very, very, very last step is going to be, and you, as I mentioned, you really don't have to do this, because you can do the rest of that in your head. 6.41 ohms, 20 volts. Okay, and that was replacing those. Okay, so that's the first step, is to get down, first steps, is to get down to a simpler circuit where you know all the voltages and currents. Okay? Now, one thing that I like to do is I like to make, and I need to make sure I'm going to be on camera, I like to make a little table. And the table looks like this. VIR. Let me just write delta VIR. If you're doing power, you could put another one off the end there. And so at the very beginning, 20, 5, 2, 4, 1, 6, 10. 20. And then resistances, that's the battery here. So it's really 5, 2, 4, 1, 6, 10. This is going to be a really, really big table, by the way, because I made it a very big problem. Okay, and once I find the voltage difference or the current, I can fill these in. And I can use Ohm's law to complete them if I have two of the values. So I've just listed all those. And every time I make a new equivalent one, I'm going to put it in here. 0.789, 4.789, 1.41. Look at all these. And again, most of your problems will not have this many steps. But this is the way to do it. So I know you can simplify resistive networks and get down to that. That should be really, not, I won't say straightforward, but pretty easy. Okay. Now we're going to work backwards. Well, okay, this is 20 volts higher than this. That is connected there, and that is connected there. So this is 20 volts higher potential than there. So I can write down here for my 6.41 ohm resistor, 20 volts. I definitely know how much voltage is across that. And I can use Ohm's law. 20 divided by 6.41 is 3.12 amps. Well, if 3.12 amps is going through there, 3.12 amps is going through there. 3.12. Okay. And by the way, sometimes, really up here, I'm just talking about the battery, but this equivalent resistance, 6.41, is the resistance across connected to the battery. So sometimes we'll write it like that. Okay. Now, I want to work backwards. If I know that this current is 3.12, then I know the battery current, the current coming out of the battery is 3.12. So I say on this, what does that mean in this circuit? Well, I know the current coming out of the battery is 3.12, so it must be the same there. And it must go through there, and it must go through there. Hey, well, look. Now, for the 5 ohm resistor, I know the current, 3.12. For the 1.41 ohm resistor, I know the current, 3.12. And I can use Ohm's law to solve those. So when I do that, 3.12 times 1.41 equals, I did that wrong, sorry, 3.12 times 1.41 equals 4.399. I'm just going to say 4.4 volts. Okay? And then I can use this, or what I could do is I could just say, well, the total voltage is 20 minus 4.4, and you should end up with the same number, 5 times 3.12, or 20 minus 4.4 is 15.6. Does everybody understand? 20 minus 4.4 equals 15.6. 20 minus 15.6 minus 4.4 equals 0 is another way of doing it. Kirchhoff's loop or voltage rule. Okay, so now I know the voltage difference between here and here, and the voltage difference between here and here. Well, look up here. Let me get rid of that. Between here and here, this voltage difference is between that wire, this connection and this connection. So I know the voltage now across the 2 ohm resistor. It has to be the same as the voltage across that virtual 1.41 resistor. So 4.4 across the 2 ohm resistor, 4.4 volts, and 4.4 volts across the 4.789 resistor. So I just keep working back. So now I can use this. So you can see what's going to happen is you find 2 values and you find the missing value. Okay, now I know the current. And then I can use that and this to figure out, working backwards, what some of these currents are. And then I can find some voltages, and then I can put it on there. So I'm going to take those next 2 steps. It's like a, I don't know, Sudoku or something like that. So if I do this, voltage divided by R, 4.4, divided by 4.789, is a current of 0.919 amps. Okay, so 0.919 amps going through there. And then that voltage, 4.4 divided by 2, is 2.2 amps. Okay, so this is 2.2 amps. And before I go any further, look at this. 2.2 plus 9.19 should end up being about 3.12. 3.12 comes in here and splits into these two parts. It should add together. What I'm doing is, every time I see parallel resistors, they have the same voltage as each other. Every time I see series resistors, they have the same current as each other. So if I keep that straight, it will allow me to keep working up through this. I'm going to go very quickly through the next ones. Now I know the current through the 4.789, and remember that replaced this. So they have the same current. Series resistances have the same current and the same current as the equivalent. So this is 0.919 in both of those. 0.919 is the current in the 4 ohm. 0.919 is the current in the 0.7891. So I take that, multiply it by 0.789, I get the voltage across, 0.725 volts, 0.919 times 4. The voltage across the 4 ohm resistor is 3.676. Okay, so now I know the voltage difference here, and I know the voltage difference here. Now we can come over here. If the 0.789 resistor, which was an equivalent resistor, the voltage is, where'd I go? 0.725. Well, this voltage has to be 0.725. So now I've got all these other ones, the 1, the 6, and the 10, all have the same voltage across, and I can solve for the current. So at the very end, I will know every voltage difference across the resistor, and I will know every current. I'm going to do it really quick. 0.725 divided by 1, 725. 0.725 divided by 6, 0.121, and 0.725 divided by 10, about 0.7073. Look at that. That's a lot of stuff we just did. What you do, simplify and redraw, simplify and redraw, simplify and redraw until you get something where you can figure out. I could have stopped there because I know 20 divided by 6.41, and I could find that current. It's got to be the same for both of those. I didn't really have to do this one, but it's kind of nice to get that total equivalent resistance. Okay, then you work backwards. Parallel resistors have the same delta V as each other, but they also have the same delta V as whatever you replaced them with. So here, when I replace these with this, if I know the voltage across this one, 0.789, I know the voltage across each of those. Series resistors have the same current. So for example, sample here, I had 3.12 amps going through this equivalent thing. Well, it came from these series ones, so 3.12 must be going through each of those. And when you work backwards, finally, I could take that table and I could label every element in here and tell what the current through it is and the voltage difference across it is. This was a blitzkrieg tour of the of how to analyze resistive circuits relatively confidently. I hope it's helped.